We have a funny little quirk of trigonometry and angle relationships in this particular example. I have two triangles here, and they clearly do not look the same, but both of them have a side that is 10 units long here. Both of them have a side that is 8 units long here, just one is tipped that way, one is tipped that way. And they both have a 50-degree corner. Now, if I were to put an alpha here, down here, in this triangle, alpha is across from the 10. In this triangle, alpha is across from the 10. They're set up exactly the same. So I'm going to apply sine law to this and just see what happens. So I have sine alpha here over 10. And then I would have sine 50 over 8. Now if I set it up in this triangle, I would have sine alpha over 10 equals sine 50 over 8. It would look exactly like that. So I'm just going to work that out. I will need sine 50 in degrees. Gives me 0.766. And 0.766 divided by 8, that can't be right, 0.766 divided by 8 gives me 0.09575. Multiply both sides by 10. So that will be 0.9575. And now I need to arc sine. And if I hit that on the calculator, I get 5.49 degrees. So these triangles are obviously not to scale. If that's 50, that can't be. I think I typed that in wrong. Oh, I forgot to multiply by 10 in my calculator. Let me try that again. Sine of 0.9575 is 73.24. I like that better. Okay, start again. That angle there, 73.24 degrees. If I check to make sure everything's proportional, 73 is bigger than 50, so that side should be bigger than that side. And it worked out that way. Now, here's the catch. That angle is less than 90 degrees. If I look at these two alphas, right, which would have generated this exact same setup for both triangles, this is the one where alpha is less than 90, right? 90 degrees is square, and this one is less than that. So I've successfully figured out this one. 4 degrees. What about that one? It must be solvable. And it's clear that that angle is not 73.24. This is bigger than 90 degrees. So I need an obtuse angle to put in there. But this is all my calculator spat out. So you're going to have to remember that thing about arc sine, where when you call arc sine, it ends up generating two solutions. I'm just going to sketch the sine wave for you for a minute. I'm going to remind you that sine peaks at 90 degrees and it crosses the x-axis at 180 degrees. So I got to this line here. Sine alpha is 0.9575. Now that on the graph, that's an x value, that's a y value. So y value of 0.95 is around here somewhere. If I look across, there's a solution right there. That's at 73.24 degrees. There's another solution here. That solution there is bigger than 90, less than 180. That's exactly the kind of angle I need to in this triangle for this solution. So you're going to have to think back to the topic of trigonometry of obtuse angles. And you're going to have to look at this particular diagram and recognize that by symmetry, this distance here and this distance here are identical. So your first solution was go from 0 to 73.24. Your second solution has to go from here to here. Now, do you see that that distance is 180 back up this much? If I put that into the machine, I end up with 106.76 degrees. That's the value of this alpha here. So anytime you pull an arc sine, you move this over here, you have to do the two solutions. It's just like when you have x squared equals 9. It's easy to say x is the square root of 9, so x is 3. But that's not complete. When you pull a radical to break a square, you must consider plus or minus that option, plus or minus 3. So you had to sort of train yourself to remember this about squares and square roots. You're going to have to train yourself to remember this about arc sines. Anytime you move a sine to that side, there are two solutions. Sometimes the second solution doesn't make sense. Sometimes it's a perfectly valid option. You have to look for them and then test them. We're going to clear this off. We're going to try an example and see if we can spot the ambiguous case. That word there, before we get too far into it, ambiguous. That prefix, A-M-B-I. I think the only other word I can think of that has that start to it is ambidextrous. Now that word means you can write equally with both your left and right hands. So you are both left-handed and right-handed at the same time. So this word here, ambiguous case, means that this triangle could be a triangle with an acute angle here or a triangle with an obtuse angle here. And this setup is both. So you're going to have to hunt to make sure you can narrow down which one it is. If you're being ambiguous in conversation, it would be like somebody asks you if you're going to come to their house on Friday, and you so maybe we'll see. You didn't say no. You didn't refuse the invitation. But you also didn't say you were coming. So you're being ambiguous. You have left room to be both of those things in the invitee's mind. Enough wordplay for today. Let's try and triangle this thing here. So I've got a sine law set up there. Sine of alpha over 8 be sine of 30 over 4. Oh, I need sine of 30. Just get that from the calculator. I think it's 0.5. .5 divided by 4 is 0.125. And multiply both sides by 8. Eight times 0.125 is 1. I'm going to throw my arc sign on there. And I come up with 90 degrees. So, diagram's a bit deceptive. 90-degree corner should look more like this. If you draw it to scale. So you go to check your second solution. Here's my sine wave. There's 90 degrees. Y value of 1 would be here. And if I scroll across, that's right at the peak. Now, if you keep scrolling across, there isn't a second solution there because there's only one peak. So in this particular case, when you set up your arc sign and you get exactly 90 degrees, this question is not ambiguous because you happen to land on an exact right angle triangle. So not ambiguous. There's only one solution. And you can see that because scrolling across at a y value of 1, you only cross the curve in one place. So this is the only triangle that's possible with those particular numbers. Okay, another example. I have an angle across from a side and an angle across from a side. So that's another sine law setup. So sine of alpha over 11 would be sine of 38 over 5. So I'm going to need to sine 38. 0.616 by round. Sine alpha over 11. 0.616 divided by 5 gives me 0.123. It's a fun number. Multiply both sides by 11. And I get 1.34, 1.354. Now if you're familiar with sine, you might already have an alarm bell going off. But if not, we'll just sort of mindlessly arc sine both sides. And if you try to do that, you end up with an error. So this particular triangle actually can't exist. If I were to try and draw it to scale for you, you have a side here of unknown length. It can be as long as you like. And then at a 38-degree angle, I start drawing something that is 11 units long. Now the thing that's happened here is that the third side that's only 5 long isn't actually long enough to reach the ground. So this triangle can't actually close based on those numbers. This angle is too big, or that side is too short in order to make this work. So this one is not an ambiguous case either, because it has no solutions. Let me just write that down so you can see it. Not ambiguous because there are no solutions. Okay, so we have an example where there is one solution exactly, which is not ambiguous because it has one choice. We have a solution here that has no answer. That's not ambiguous because the answer to it doesn't work. So we're going to need an example where it is actually two triangles, and you have to figure that out. So once again, another sine law setup. The sine of alpha over 13 will be sine of 42 over 9. I'm going to need the sine of 42. Sine 42, 0.669. We'll have to do those two things divided each other. Nine is 0.074. Multiply both sides by 13. I get 0.967 if I round. It's very squeaky today. Okay, and I need to arc sine. Let's throw that across the equal sign, and I end up with 75.13 degrees. So that is a perfectly acceptable answer for a perfectly acceptable triangle. But I'm going to have to remind myself that unless this comes out as 90 or it comes out as error, I have to check for the obtuse angle solution. Right? I can see the way I've drawn it, an acute option is possible. There it is. I need to find the obtuse version. So draw myself a sine wave. I'm going to do it a little bigger this time. And we're going to remember that the peak of a sine wave happens at 90. The x-intercept happens at 180. And I was hunting for a y value of 0.967. That's about here somewhere. Almost 1, but not quite. Which means if I scroll across, I'm going to hit this curve almost at the peak, but not quite. I'll hit it once here, and I'll hit it once here. Now I already have the location of this solution, right? This length here is 75.13. To find this solution, I'm just going to drop a little thing down here. I'm trying to get to that point here. I need this length. I don't have that length, but I do know that from here to here is 180, and from here to here has to be 75.13 because this shape is symmetrical. I'm just going to draw that in there. So I want this distance I have this and I have this. That's 75.13. This much is 180. And I don't know what this is. So if you just use a little logic, if this piece and this piece have to add to 180, then this piece here is whatever's left over once I take 75.13 out of 180. Try that. And I end up with 104.87. So what I figured out is that a triangle drawn like this is perfectly acceptable to have a side length of 13 and 9 with a 42-degree corner here, as long as that side, or that angle, sorry, is 75.13 degrees. But it's also perfectly valid to have a side that's 13 with a 42-degree angle across from a side that's 9 long, as long as this angle here is 104.87. Both solutions are valid. You could do it this way, you could do it that way. So this particular example is ambiguous. This setup is both of these triangles, the one with the acute corner and the one with the obtuse corner. Now I'm going to clean this off now that we've got an example that we know is ambiguous, and I'm going to try using cosine law on it. So you can see that the two solution thing pops up even when you're doing cosine law. Just a little reminder, cosine law is c squared is a squared plus b squared minus 2ab cos of whatever angle you're working on. And this angle and this side have to be opposite each other. So if I look at this particular setup, I know an angle here and I know a side opposite to it. So this is going to be my C, this is going to be my omega. If that's C, this is either A or B. It doesn't matter. So I'm going to make it A, which means that this unknown side here is going to be my B. So B, I don't know this yet. Okay, so I'm going to start filling in numbers. C I set as 9. A I set as 13. B I don't know yet. Minus 2. A I said was 13. B I don't know yet. And omega is 42. So I've got some squaring and some multiplying and a cosine to evaluate. So I'm just going to do all that in one line because they don't interfere with each other. 9 squared is 81. 13 squared is 169. 2 times 3 is 26. And the cosine of 42 is 0.743. Okay, I'm going to do 26 times 0.743. So I get subtract 19.322 if I round, with a B still attached. All right, now This equation has a b and a b squared in it. It means it's not linear algebra anymore. As soon as you have a thing and that same thing squared combined with addition and subtraction, you can't just move stuff over to solve for b. You have to use some nonlinear techniques. And most likely, the only nonlinear techniques you know are either factoring or the quadratic formula. Now, to do factoring or quadratic formula, you have to have these in a certain sort of arrangement. You have to have some number multiplied by some number by the thing squared, some number by the thing not so squared, some number without a variable at all, and it all has to equal 0. That's ready for quadratic formula or factoring. So I got to bend this a little bit. So first off, there shouldn't be anything on this side of the equal sign. So I'm going to have to subtract 81 from both sides. Now 169 minus 81 gives me 88. Plus a b squared minus 19.322b. You don't have to get them in exactly this order, but it helps you to use the quadratic formula. Put your b squared first, your thing that's not squared second, and your number with no letter attached at the back. So I've got an a value here. A value is in the number attached to my squared thing is 1. So there's one b squared there. The number attached to my not squared thing is negative 19.322. And my number without a variable at all is 88. Now, if I have an equation in that form, I can use the quadratic formula, which, conjure it from the archives, the variable I'm solving for will be the coefficient on the not squared thing, plus or minus the square root of that same coefficient squared, minus 4 times the coefficient on the squared thing, times the coefficient on the thing with no variable at all over 2 times that coefficient. If you don't recognize that, go find a tutorial on the quadratic formula to see where that came from. This is just a forever fact. It's, I don't know, 1,000 years old. So if I've got these numbers, I can just drop them in there. Negative 19.322 would be 19.322 plus or minus the square root of negative 19.322 squared minus 4 times 1 times 88. And I'm sorry, this is going to be on my face here. 2 times 1. Maybe I can. There we go. Just ruin my posture. That'll be fine. Okay, so 19.322 plus or minus 19.322 squared is 373.34, or 340 if I round it. 4 times 88 times 1 is 352. So B is 19.322 plus or minus the square root 373.34 0.34, subtract 352 gives me 21.34. I'm going to have to square root this now. .620 if I round. Now, this is where things get interesting. I have a plus minus in this equation, which means I'm going to get two solutions. One of them is 19.322 plus 4.62, or it could be 19.322 subtract 4.620. That's definitely on my face now. So if I figure out this one, 19.322 plus 4.62 is 23.942. I'm just going to divide it by 2 so we cover it around the space. This whole thing, if you work it out, gives me 11.971. Or if I do 19.322 subtract 4.620 and divide by 2, I get 9.351. Okay. So if I were to draw this diagram twice using this length and this length, I either have 13 42-degree angle, a side length of 9, and a side length of 11.971, because that's where B is on my diagram. Or I have a side length of 13, a side length of 9, a 42-degree angle, and this side is 9.351. Now I'm gonna try and remember. I think that this was a 73-degree angle. I think you'd have to rewind back to see it. And then this one was 104, I think. Maybe that means this was 75. And this was 105-ish. Doesn't matter exactly what it was. They were approximately that. If you check, this angle up here, this angle plus this angle plus this angle has to be 180. So if I figure that out, 180 subtract 42 subtract 75, that leaves 63 degrees for this angle up here. If I do it for this one, 180, take out 42, take out 105, I end up with 33 degrees up here. So I have the biggest angle across from the biggest side, and I have the biggest angle across from the biggest side. So it all worked out that way. Both of these are options, but I couldn't tell until I'd gone through all this math. Now, I'm sure you're looking at this. Well, it's on my face here. And you're thinking, wow, that's a hot mess. And you're right, that is a hot mess. Don't do it with cosine law. That's why all these things he was always starting with sine law, because the math didn't require a quadratic formula, didn't require all this management, and you still ended up with these two solutions with about half the work. So why did I do cosine law at all then? Well, just to show you it could be done, but also to point out this thing, this plus or minus. The plus or minus square root comes from undoing a square at some point in all the algebra here. And you had to train yourself that anytime you broke a square, you needed a plus minus. The point of this is that behavior, having to use plus or minus to break a square, is the exact same type of requirement when you had to do two solutions for sine and arcsine. So anytime you're using sine law and you spit out an angle, you have to check to see if maybe an obtuse angle is also an option.